All right, so let's get started. Remember last week we talked a lot about, in the last 2 weeks actually, a lot about the physical layers, and last thing we did last week was to start to talk about something called error detection codes. And this is a crucial part of the link layer that we will talk about increasingly today. So we will talk first, finish off this part about error detection, and then start to talk about retransmission protocols and how to do error control on higher layers, starting with the link layer. Okay, so short review. We talked about error or block encoders or block codes. And block encoders is a device that takes k input bits and produces n output bits. The input bits are called information bits, sometimes called information bits or information information bits. And if we block them together in these k bits, we get this information word or information block, or has several other names. But these are the bits that we would like to convey over the channel somehow. And then we have the coded bits and the code word. And the code word is the output vector. So we have an input vector and an output vector. And since we have k possible inputs, we have 2 to the power of k possible input patterns. K input bits, 2 to the k possible inputs, which means that we have 2 to the power of k possible outputs. And if we put all the possible outputs into a set, we call that the code, or sometimes the code book. The code rate is the ratio between the number of input bits to the number of output bits. And this is something that somehow measures the overhead which is introduced, the number of extra bits that are produced here. And we would like to keep the code rate relatively high, but still have good performance. Then, so this is in general what's true about block codes. Now, we would most often use systematic and linear block codes. So what are those? Well, systematic simply means that the first k bits in the code word is exactly the input bits. Okay, so this is a copy of the information bits in the beginning. And then we have some check bits or parity bits at the end. Remember, we have k input bits, and therefore we have n minus k parity bits. The whole thing is n bits. A linear code, essentially what it means is that if we take 2 code words, any set of 2 code words here, could be the same code word, doesn't need to be unique, but any 2 code words, and we add them together, we get another code word. Okay, so by adding code words to each other, we stay within the set. So basically we take 2 code words, so CK and CL are in the set C. Then if that is true, then CK plus CL is also in C. And okay, we add all the components in these vectors modulo 2. So this is a binary vector, this is a binary vector. When we add them together, we get a binary vector. If one wants to visualize this, how this works, we can take a small code with just 4 code words. And then by this property, we know that the 0 code word will always be in the code. Okay, why is that? Well, if we take CK plus CK, we get the all 0 code word. And that has to be in the code word if it's a linear code. Okay, so we know that the 0 code word would be the code word consisting of all zeros, that's what I'm meaning, will be part of the code. And we can say that this is C1, okay? And then if we take C1 and then add on the other code words, we get 0 plus the code word, and then we will end up in that code word. So from 0, if we add on C2, we will end up at C2. If we take 0 plus C4, we will end up at C4. 0 plus C3, that we end up at C3. Okay, this is true for any code. But the beauty of a linear block code is that we can complete arrows between all these code words, where what we go from one code word to another is just adding what's on this arrow. So going from C2 to C4, we add C3. Okay, which means that C4 is C2 plus C3, or it's just C4, or it's C3 plus C2, or it's C3 plus C4 plus C3. We can get here many ways, right? But we never fall off the grid here. By just adding code words to each other, we stay in there. Okay, so then we talked about the Hamming weight of a code, or Hamming weight of a binary vector, and that's just the number of ones in the binary vector. The Hamming distance between two binary vectors is the number of positions in which the two vectors differs. So the Hamming distance between u and v is the number of bit positions where u and v differs, which is the same as the Hamming weight of u plus v. By adding u plus v, we get a 0 entry whenever u and v has the same bit, and a 1 bit when they have different bits in that position. So the Hamming weight of the sum of u and v is indeed the number of ones, the number of positions in which u and v differ. So why is, okay, and this is binary addition, addition modulo 2 or XOR, it follows these rules. And why is this important? Well, the minimum distance of a code is something which is an important property of it, and we essentially would like this to be big. Okay, and the reason for this will become clear shortly. But the minimum distance, what is it? Well, we just take two code words and we measure the distance between them, and then we find the pair which is closest to each other. Now we cannot choose CK equal to CL because then we get 0, so that's meaningless. That's the same for all codes. So we have to take two different code words here and find the smallest distance between them. If it's a linear code, then we know that, I mean, first of all, we know that the Hamming distance is the Hamming weight of its input, okay? So in this case, it will be like this. That's true for all codes. But then for linear codes, we know that CK plus CL is some other code word CJ, or, you know, it's in the code. So if we want to find a minimum distance for a linear code, we simply look at the weights of all the code words. And the smallest non-zero code word weight is also the minimum distance. So this is a nice property. We don't have to search through all pairs. We can just look at the weights of the individual code words. All right. Now, so if C is the transmitted code word, then the receive pattern is C plus an error pattern. And remember that when we add modulo 2 here, we can interpret this as we flip the bits in C in which E has ones. Okay, so I'll say that again. We flip the bit positions in C where E has a 1 in that position. And in the other ones we don't. Okay. So the Hamming weight of the error pattern is the number of errors that we would see in the code word. And then the final review slides here. So for error, okay, so this is the heart of error detection. Okay, so this is a crucial thing. This one you need to remember. A receiver inspects Y and it declares that no errors have occurred if the received pattern is a code word. Okay, so that's how we do error detection. We know that the transmitted bits is a code word. So if the received bits are not a code word, then something is wrong. Okay, and we use that fact by declaring that now an error has occurred. This we will be able to do with 100% certainty. If the received word is not a code word, something bad has happened. Okay. The opposite, however, is not true. That is, if the received word is a code word, then we're not quite sure that things are okay. And the reason for this is that the error might be such that it goes from one code word to another code word. And those type of errors we cannot detect. Nevertheless, for a code with a minimum distance d-min, we are guaranteed that all error patterns with the weight which is less than d-min are guaranteed to be detectable. Okay, so if we have, say, a code with minimum distance 3, that tells me that all 2-bit error patterns will be detectable. And the reason for this is that if we take a code word and flip it in 2 positions, we cannot reach another code word because the distance between 2 code words is 3 at least. Okay. So clearly we would like to have codes with high minimum distance, because if you look at the most probable error patterns on a noisy channel, these are the 1-bit error patterns followed by the 2-bit error patterns followed by the 3-bit error patterns and so forth. So the most likely error patterns we would see on a noisy channel have low weights. Okay? So if we can protect ourselves against that, we have protected ourselves against a large, the most likely error patterns here. And therefore having a good minimum distance is nice. Okay, now can we say something more about detectable and undetectable error patterns? Yes, we can, at least when the code is linear. So we will use this. So suppose C is the transmitted code word and E is not equal to 0. So an error has occurred. Okay? So a non-zero error pattern. Then if C plus E is in the code, then we say that E is undetectable. Right? So for a given C, certain error patterns are undetectable, namely those that we take C, we flip a number of bits in C according to E, and then we end up in another code word. Okay. Then these errors would never be detected. Okay. Because the received word would be code word, we will accept this as being error-free, even though it's not. Okay. So if this is true, this condition is true, then we say that E is undetectable. Now for a linear code, that means that E is in C. And why is that? Well, we know that C plus another code word will be a code word. Hence, if E is in the code, then this sum will also be in the code, and that will not be detectable. Did you follow that? Okay, it was a little bit quick, right? So, yeah, so for instance, if we have if we go back, it's actually easier to see here. Now, so this is a linear code. Okay, we have 4 code words like this. And to get from one code word to another code word, we follow this line here, which says that we should add, if we're in C2 and we want to go to C4, we add C3 to it. So if we think of this as an error pattern, and this as the transmitted code word, we would end up in another code word. If this is the transmitted code word, we would end up in another code word if the error pattern is either C3, C4, or C2. And these are the only possibilities. Any other error pattern will fall outside the code word. So did that explain it? Yeah, exactly. So if we have a description of the code words, we know what the undetectable error patterns are. And in fact, we know that, so that tells us a lot. Okay, but also we should notice here, okay, so let me go back actually. So this is actually easier to show here. Now, one of these code words, either it's C2, C3, or C4, will be the minimum weight code word. Okay. non-zero code word. C1 is 0, so we don't count that. So one of these code words here will be having a weight which is equal to the minimum distance. And then we see that there is such an error pattern that we can go for. Suppose that C2 is this. Then for sure C2 is an undetected error pattern, right? But there are many other code words with the same weight. There are many other error patterns with the same weight as E2 that point somewhere else, like this. And that will not be undetectable. So what I'm trying to say now in a very convoluted way, I realize here, is that if we have a certain minimum distance, it will tell us that certain error patterns are guaranteed to be detectable, but it's not if and only if. So there are many error patterns which has a weight which is bigger than the minimum distance that are still detectable. Okay. And it's not hard to see by just listing the error patterns for a simple code, and you will see this quickly. Okay, so to summarize here, a good code, what do we want? We want that to have high minimum distance, because then we can correct many of the more likely error patterns. And then it should also have a good burst error correcting capability. We haven't really talked about this, but I just mentioned it here anyways. And good ability to detect completely random error patterns, which is known as a high error coverage. We have concentrated on talking about high minimum distance here, and have chosen not to talk about the other things because it will require more time than what we have to our disposal. Nevertheless, we will not design error detecting codes in this class. We will just pick a few families which are used in practice and talk about them. Okay. So a good code, I think here, sure, right? A good code, a code, right? Okay, should have high rate and low encoding and error detecting complexity and so forth. Now, common codes that are used in practice are singleton parity check code, internet checksum, and CRCs. And I would say the latter, the CRCs, is nowadays the standard choice for error detecting codes. So we will talk a little bit about how they work and some of them where they are used and so forth coming now. Okay, any questions before we start here? Okay. So let's dive into the beautiful world of cyclic redundancy check codes. This requires us to talk about binary polynomials. So a binary polynomial, what does that mean? Well, a polynomial, it's some type of linear combination of different powers of an independent variable. So a binary polynomial v of x is of the form something times x to the power of something and so forth, like this. What makes this binary is all the coefficients here are binary, 0 and 1s. Okay, so that's a binary polynomial. We can think of a binary polynomial v of a certain degree n minus 1. So what is the degree? Well, the degree is the power, the highest power, where this is non-zero. Okay, so the highest power in the polynomial is the degree. Okay, so we can think of a polynomial of degree n minus 1 as a representation of an n-bit vector. And why is that? Well, if we count the number of terms in the sum, it is actually the degree plus 1. Right? A 0 degree polynomial has 1 term. 1 degree polynomial has 2 terms, and so forth. So if we have if we take an example of a bit pattern, so 1 0 1 1. And we would like to represent this with a polynomial. Let's call it g of x. So we have a binary vector g, and we would like to write this as a polynomial. Then we just think of these ones and zeros in this pattern as the coefficients of that polynomial. So the only thing we need to decide is whether this is the highest power or this is the highest power. Then everything is clear. So we will, in this course, have the convention that this corresponds to the highest power. So so this will be then something times x to a certain power. So the highest power here, what is that required here? Is it x2, x3, x4, x79? What is it? X3. Yeah, exactly. So it's x3 because we have here 4 bits. Okay, so that means that we need a degree of g of x being equal to 3. Okay, and then we just take the first coefficient and multiply that with x3. We take the second coefficient, 0, and multiply that with x2. Then the third, 1 times x plus 1 times x to the power of 0. Okay, and then we're done. Right? And we can simplify this by just writing this as x3. I don't need to keep that, plus x plus 1, like this. Okay, it's just another way to encode these bits, right? And it's not obvious why this would be any good at this moment, but it's just another representation of bits. Okay. A little bit peculiar perhaps could be if we have another pattern, let's call it P, where we have 0, 0, 1, 0, 1, 1, for instance. Now, what polynomial would that correspond to?
3 again.
Yeah, so it will be the same polynomial, right? Because we have 2 leading terms which are 0 here. So if we want to keep track of this, we will insist on writing these as, let's see, we need x5 and 0 times x4. And then we have the other things here. If we really want to keep track of how many bits we have in the original pattern here. But it's sort of understood that we can do this, right? Okay. Now, if we have these type of polynomials, this one, g of x, and I would like to add some zeros to the right of this pattern. So if I want to go from g, which is 1, 0, 1, 1, to some pattern, let's call it, now we used p, let's call it, I don't know, x is bad, h, right, okay. Now suppose I wanted to write this with 2 extra zeros here to the right. What is the corresponding polynomial to that? Well, we can write out the numbers, but can we write this in terms of g of x? I claim we can do this if we add something here, a factor. Ah, good. x2, right? Because with x2, we increase the degrees of all of these, which is the same thing as we add some zeros to the right of the bit pattern. Okay. So maybe this is a reason why we want to do polynomials. It's easy to do shifts of bit patterns by just multiplying with the corresponding power of x. Okay, so that is actually quite useful in the math we will now develop. Now, sometimes I get the question, so what is x here? And x is just a placeholder. It has no, we don't put in x equals 2 or something into this. It has no meaning for us in this sense. So think of x as just a way of keeping track of where the bits should be in the bit pattern. Okay, so x itself has no particular meaning here. Okay? All right. So then we know here then that if we take x to the power of m times v, we get a polynomial corresponding to appending m bits to the right. If we want to add 2 polynomials, it's the same, except now, since it's binary polynomials, we add the coefficients modulo 2. Okay? So the addition of two binary polynomials should also be a binary polynomial. So then if we take, I don't know, yeah, let's just do this, v plus q, then we take the corresponding coefficients in front of the nth power of x, and we just add them, but there is a modulo 2 here. So don't forget that. But with that, how about this addition? What is gx plus gx? What is that? Inverse?
Inverse gx.
Not quite. It's g plus g, so it would, whatever coefficient there is in front of a power, say n, we would have the same bit here, right? Did I write this correctly? Yeah. So this would be equal to a bit plus itself modulo 2 is?
Is that a flip it?
No, it's not.
0.
0. This is equal to 0. If g is 0, then it's 0 plus 0, that's 0. If g is 1, it's 1 plus 1 is 0. Okay, so this is actually 0. So addition is the same thing as subtraction when we do with binary numbers. Okay. And that turns out to be important now when we want to do the CRCs here, how to calculate those. Okay, any questions on binary polynomials? Okay. So again, we will not use them to find roots and stuff like this. So that's, don't worry about that. It's just what we want to do is use polynomials and we want to divide them. That's the thing we would like to do here. Okay, so binary polynomial division. So what is that? Well, binary polynomials can be divided just as regular polynomials. You've probably seen polynomials over the real field, where the coefficients are real numbers. And perhaps you know you can divide polynomials with each other. Have you done that? Yeah, exactly. So if it's the same thing here, we can do this also with binary polynomials, except when we do the calculations on the coefficients, we use modulo 2 addition, which is also modulo 2 subtraction, instead of the regular plus and minus that we do when we do and multiplications we do when we do polynomials. Polynomials for the real field. Okay, so the key thing is here that if we have a polynomial, let's call it P, we can always write that as a product of G and Q plus R, where the degree of R is less than the degree of G. Okay, so this is similar to regular division, I would say. So, for instance, we can write 7 as 3 times 2 plus 1. Right? We can always do this. And if you see here, 7, 7 is the product of 3 and 2, and here we have the remainder. So we see here that 1 is given that we decide on what G is, in this case 2, then we know that the remainder must be less than 2. 1 in this case. It could also be 0, who knows. But anyways, we can always write a polynomial in this form, where if we want to call these names, this is the dividend, this is called the divisor, this is called the quotient, and this is the remainder. And if G, the divisor here, is non-zero, then it makes sense to divide the left-hand side and right-hand side with G. So then P divided by G, this is the division that we would like to carry out, results in the quotient plus the remainder divided by G. Okay. So the key thing why this is important, or why we do this at all, is that these type of divisions of binary polynomials can be done very, very efficiently in hardware. Okay, so it's very simple circuits to do this, which is great because if this could be used as your encoding and decoding mechanisms, we have an efficient hardware implementation of this. So sorry for that sound. I need to do something about that one of these days. Okay, so we can do that by hand, which is what you do when you're at the exam, right? Or in problem-solving sessions. Well, you design this in your future life as a hotshot electronic engineer, you use digital circuits for this. Right? So now CRCs, what are those? This is like the workhorse for error detection nowadays, I would say. So it's a quite important concept in itself. So an NK CRC is defined by generator polynomial. So what defines the code is this polynomial G. That's all we need to know. Okay? G is the definition of the code. So once we have G, we know everything there is to know about the code. Or rather, we can generate code words, we can decode code words, and check if a receipt pattern is a code word, and so forth. Okay, and the degree of the generated polynomial is n minus k. And remember that k is the number of input bits, and n is the number of output bits. Okay, and actually n minus k is the number of check bits. Okay. So the generated polynomial, the degree of it, determines how many check bits we have. Okay. And CRCs, as you will see later on, are systematic linear codes. So if they are systematic, if we can just calculate the check bits, we're done. Okay. So let's see how we do that. So k information bits are then represented by a polynomial. Let's call it I for information. Then the n minus k check bits, how do we find them? Well, we find them by finding the remainder by dividing xi, left shift where we put in n minus k zeros at the right, and divide that by the generated polynomial. So we'll go through an example shortly here to show the mechanics of this. But this is the fundamental equation that we take the information bits. This is the input, right? Input. And what do? First of all, we put in a number of zeros to the right. And then G was given to us. That is our, that defines the code. And then we write the left-hand side as G times some Q plus R. And actually, the output here, R, is what we're looking for. This defines the parity bits, or the check bits. Okay. We don't care about Q. Q is just a side effect of the calculation here. So input, left shift, divide by G, keep track of the remainder. That's what we want to do. And once we have the remainder, we basically stick that at the end we add that to the information bits, and then we have the code word. Okay, so let me start in another attack here. So the code polynomial is the information bits where we put in zeros to the right plus the remainder polynomial. Which means that the first part of the code word is just the information bits, and the last part of the code word is just the check bits. So R of X, which encodes the check bits, are placed here. Information bits, check bits. And then it's easy to show that this is Gx plus Q, Gx times Qx. And why is this? Well, we know that the code polynomial is x n minus k times I of x. Okay, So this is the input. And then we add on to that the remainder. Okay. What do we know about this part? Well, we know that this can be written as, this part can be written as G times Q plus R. So this is G times Q plus R. That's how we found R to begin with. Okay, so we can write this as G of X, Q of X plus R plus R. Okay, and what is this equal to? If we add the two last terms to each other, what do we get when adding these terms to each other? 0, exactly. So this is G of X times Q of X. Okay. And this is the cool part of it. Now, so if I want to check, actually from this we know that C of X, if I divide that by G of X, I get a 0 remainder. Remainder I might get, but remainder, yeah. Okay. So a code word, I can check whether a polynomial is a code word or not by simply dividing by G and checking whether I get a 0 remainder or not. If I get a 0 remainder, it's a code word. If I don't get 0 remainder, it's not a code word. So the encoding and decoding process is the same type of circuitry, right? And that is one of the strengths of these CRCs. Okay, so it is not difficult to show that this is a linear code, and for sure it's systematic code because we know that the information bits are in the beginning of the code word. Okay. All right. Yes. So a short example of this. Suppose we have somebody has given us G. Okay, so we want to. This is defining the code. Somebody has given this to us, and we can write that in the following form. In binary, would look like 10011, 1011. Okay, so this is defines the code, and we would like to encode these information bits. So it's a bunch of ones and zeros. So the first thing we do is to multiply with x to a power, and the power here should be n minus k, which is the, the degree of g of x is n minus k, and the degree we see is equal to 3 in this case. Okay, so given G, I know how many zeros to put in. Okay, so let's do that. We put in the magenta zeros here. And then our task is to write this in the following form. G was given to us. We need to find Q. Q we don't care about, but actually what we care about is the remainder. Okay, so let's calculate this. Okay, now, dividing polynomials can be done in many different ways, and there's many different ways one can do it in the wrong fashion. So let's do it right, and here's how to do it. We would like to do what's known as long division in a particular pattern. Okay, and it's not so difficult. Once you've done this 5 times, you know how to do it. So it's not rocket science. But if you want to invent this at the exam, it is rocket science, right? Yeah, so, you know, do it a few times before the exam, you'll be fine. Okay, so the first thing we want to do then is to put what we would like to divide, the left-hand side of this equation, at the top here. And now what we want to do is to find, using g of x, we would like to find Q and R. Okay. So the first thing we do is then to say that, okay, we search for the first one in the input pattern, and it happens to be the leftmost bit here. And then we stick in G here. Okay. And then we add. And add is subtraction. So whenever there is two ones above each other, you get a 0. When there is a 0, 1 or 1, 0 or 0, 1, you get a 1 and 1, 1. So like this. So we add them together, and then we get this black pattern. Okay. Now we identify where is the position of the leading one, and then we place our generator polynomial just below it, so that the leading one of what is left here lines up with the leading one of our generator polynomial. Okay, and then we continue this, and we do this, and then we get a new pattern, the black pattern here, and we just continue here to identify where the leading ones are and line up the g of x accordingly. And we keep on doing this, and it looks quite boring here, but here we got lucky. We got a bunch of zeros here. So now we can skip further and then just line up with the leading one here, where we put our g of x there, and we just continue, continue, continue. This is tedious, but it's not difficult, it's just tedious. Right? And continue, and now we're starting to get interesting here. Now, because we're getting close to the end here. And here we just put in the next g here. And here we got this now. And now it's interesting here, because now there are no leading zeros, no leading ones left here in the black pattern. Everything is now non-zero is in the brownish thing here, brown-orange. So the next, the generator polynomial will not fit inside this pattern. So actually what is left here is the remainder. Okay, so I'll go back. No. Okay. Okay, so what is here is the corresponds to R of x. So basically these are the bits 1, 0, 0. So that's our remainder polynomial. And then we just stick it into the code word. So the code word consists of the input bits, information bits, plus the remainder, where we have now replaced these placeholders with the remainder. Okay. So the process is take the input, add some zeros, do long division, identify the remainder, stick the remainder bits at the end of the input bits, and we have our code word. And if I completed the same encoding algorithm on these bits, I will get a remainder where we have all the zeros. So.
How do you know how many zeros first in the back?
Okay. So that has to do with the degree of the generator polynomial is 3, and therefore we put 3 zeros here. Okay. So it's this n minus k. One interesting thing here is that the CRCs only determine how many check bits we have. We can have as many information bits we like. So there is no limit to n here. So okay, so this procedure does not say, okay, you can only have 16 output bits or something like that. It works for any n, okay? Or rather, I would say it works for any, let me correct that, it works for any k number of input bits. Okay. So g of x only tells us what n minus k is. It doesn't tell us what k must be. Okay. So this is good. We can put CRCs on any length input as we like. That's also nice. Okay, so common CRC codes which are used in practice, they have names. There's something called the CRC32, the CRC16-CCITT, or the CRC1, and there is a bunch of other ones. So the CRC32 has a degree 32 polynomial, which is this one. Okay. So how many check bits is there for CRC32? How many check bits? The generated polynomial has degree 32, which is equal to the number of check bits. Okay. Okay. In general, it's good to have many check bits for performance, but it's bad from an overhead point of view. Okay. So the CRC32 looks like this, and this is used in many different standards, including Ethernet and maybe a few others that you heard of before. Okay. The CRC16 is a little bit weaker code. Looks something like this, and it's used in these Bluetooth, probably heard of, and a bunch of other might not have heard of. And then the CRC1 is actually quite trivial. It's what's known also as the single parity check code. So this is single parity check code, the one that we talked about earlier. I gotten these polynomials from our friend Wikipedia. Okay. Wikipedia is usually reliable, but not always, right? So it should be taken with a grain of salt. But in this case, I think it's accurate. However, if you do that, Wikipedia will only list these, okay, bits. It will not list the initial one. For some reason, this is also a convention which is used. So if you want to implement this, you know, don't forget the leading one. Otherwise, you would have something which is not such a nice of a code. It will still be a cyclically redundancy check code, but it will not be the one that you're looking for. Okay. Any questions? Okay, no. All right, so let's end here and take 15 minutes.